I would like to show you another algorithm for fixed parameter tractability approach to k-vertex cobble, and it is called bounded search tree algorithm. I'm sorry that my playlist is about approximation. I'm just talking about fixed parameter tractability, but this is just to make some example and show you some flavors of that. But fixed parameter tractability is just about exact solutions. And I'm not going to talk about it more than that. So here the exponent doesn't depend on k. So f of k n to the order of 1. So it is fixed parameter tractable if it can be solved in f of k n to the order of 1. And this is polynomial in n, and this is f of k. And this is exponential in k. And then the bounded search tree algorithm, which is a better algorithm than brute force solution to k-vertex cover, is that we consider any edge equal to u and v. Either u or v should be in cover, and then we guess that u is in S. We delete u and all incident edges. We decrement k. We recurse on g prime and k prime, and finally for any v we do the same thing, because if you have an edge, you have vertex u and v. So you do this algorithm for u, you do this for v, and then it is so we have n of k, and then because you remove one vertex, one edge, so you get this one, and then you remove another, and the algorithm goes like this. And so the order of complexity n to the k. Okay, so let's get back to approximation algorithm, which is my favorite, and give you another problem, which is called I'm interested to talk about cut sparsifiers, because it is the prerequisite to many of the topics that I'm interested to share, such as expander decomposition, such as sparsification, multi-way cut, all of these, multi-way cut, k-cut, vertex sparsifier, so many names, so many problems, and all of them are NP hard. We try to approximate them. So let's get back to history. Cut sparsifiers. You have seen, if you have seen Simon's Institute lectures, which is my favorite, I've seen many of them. I think I've seen all of the lectures about problems in machine learning and computer science, and the guy Bankser and Karger. Because this is a seminal work, everybody start their lectures by just introducing their algorithm. And so this is a seminal work, and this because it is historically one of the first algorithm in this area. And the epsilon cut Sparsifier is that H is a graph on the same set of vertices such that for any vertex set S, the cut of S is almost equal to cut of S And let me give you an example. This is my example. And this is almost equal to this example. And this is our H. This is our G, which is dense. Our H is sparse because we have summarized the graph somehow. And their criterion is just cut, nothing else. Because you can summarize a huge graph, billions of nodes, using some criterions. In this case, our criterion is just the cut. So the cut of this example, this is G. The cut of this example can be this. And the cut in H is this, so they're almost equal. So we go from the dense graph G to the sparse graph H. And the cut of S is the sum of the weights of edges going across the cut. So any graph has an epsilon graph sparsifier with n log n epsilon 2 edges. You've probably seen this several times. So note that the weights in H are potentially different in G. So it may be double, it may be the same, so they're potentially different. So after these guys, wrote 1996 article, some people like Spielman, this guy especially, and Tang in 2004 generalized this approach to spectral Sparsifier. And, X transpose L is is less than 1 plus epsilon error, X transpose L, Lx. So L is the Laplacian L of S. Here, L of S, Laplacian of S, Laplacian of G, Laplacian of S. So it is sandwiched between some upper and lower bound. And the graph Laplacian, I'm just reviewing. So recall that L transpose GX, this is n by n, as you have seen in my lectures several times. This is equal to I and J in E of G, omega ij xi minus xj squared. And you know that here x is in Rn, and I'll show you why we go from discrete to continuous. And so x is x1, xi, xj, xn. Okay, so you need to know that the cut of S is 1 transpose 1s. So you need to know that the cut of A and B, for example, here we have a click. Here we have another click. And we connect them with some edges. So A and B are disjoint if I just remove the blue edges. So the cut between A and B can be defined by the sum of over all the edges that going across. In other words, I is one side, J is in another side. And if you just write this, it becomes 1/4 of omega ij, and I will define what is f and fi and fj. So this is equal to f transpose the diagonal matrix minus w f. And fi is defined like this. So if xi is in A, so the same trick in any optimization. So it becomes this one, and the proof is very simple, because you just write ft df minus f transpose wf, which is equal to di fi squared minus over I minus fi fj wij, which is equal to 1/2 summation over I summation over j wij. So I'm just simplify that. And in this step, I'm just making it square. So the same trick in high school. So very elementary steps, nothing unusual. All of these steps are very natural for a high school student. So this becomes fi minus fj, which was our motivation for this trick. And so the balanced mean cut is that you care about the balance of this. For example, A and B, we want to be balanced as much as possible. So we minimize the cuts of A and B such that A equals to B, the cardinality of them equals to B. And you know that it is NP hard minimize F transpose LF. F takes -1 and 1 n, and such that F transpose 1 equals to 0. And of course, since sigma fi becomes I in A minus I in B, and this is 0. And so as usual, because it is an integer problem, we want to relax it. So relaxation. So we relax f not to be binary. I mean, now it is continuous. So minimize F transpose LF for any F in the Rn such that F transpose 1 is 0 and F transpose F in. And sorry that I'm talking about spectral clustering somehow, because F transpose LF over F transpose F is lambda. And F is the eigenvector of L corresponding to second smallest eigenvalue. And you know that if you want to minimize this F transpose LF over F transpose F such that F transpose 1 is equal to 0, once again, according to Rayleigh, this minimization problem has a very simple answer. It is lambda mean of L. So the minimum eigenvalue of your Laplacian is the solution to this minimization problem. So I want to give you another flavor of spectral clustering, because we are here and I want to complete our subject. So assume that we have decomposed it like this, and you suddenly notice that You get a block of 1. So this is the first eigenvector. You get another eigenvector, for example, this one. You get the third eigenvector, which is this one and a block of 1. And you see that you can go and do your spectral clustering. So don't forget that 1 transpose LG 1S is just your cut of S. And H is an epsilon spectral Sparsifier of G. So H is an Sparsifier of G. If for any X, now you understand why X transpose LX should be approximated by X transpose LX. So Spielman and Tang in 2004, they showed that any graph has an epsilon spectral Sparsifier with n to the n epsilon minus 2 log O1 of n edges. And of course, Batso and Spielman and Srivastava in 2009, they showed that you can reduce your number of edges with just n epsilon minus 2 edges. So a great improvement. But how do you build a spectral Sparsifier? And the answer is that you do it by effective. This is just one of the ways. There are maybe 10 different ways to answer this question. But effective resistance is natural, but it takes time. Of course, it's matrix multiplication, but still it can do something even faster than matrix multiplication. So effective resistance between the vertex I and J, so this is edge E, is just Ij transpose your Laplacian inverse 1i minus 1j. And you have heard several times that this is equivalent to electrical networks. For example, here is I, here is J, E is an edge, and is something like this. So let's move on and build a spectral Sparsifier by coin flipping. So I want to show you how you can use this effective resistance to create a spectral Sparsifier. So we first calculate importance scores for each edge, which equals to WE effective resistance of that edge. So this is effective resistance. And after that, for all edges with importance scores not more than the median, if it comes head, you just pick with probability 1/2, you double the edges. Double edge weight if it is weighted graph. And if it is tail, you just with probability 1/2, you discard the edge. Discard the edge. And this discards roughly 1/4 of the edges. And if you repeat until m is equal to n log n over epsilon 2. This reminds me the Karger algorithm, which is very, very easy. You contract it and then until you get k cuts. So it's same framework, and you just change your measure.